Good morning, everyone. Those of you at the back, can you hear me clearly? Okay, those of you on the Zoom too, can somebody confirm if you can hear me clearly? I need one person to, I need somebody to talk if you can hear me, those of you on the Zoom.
I
Yeah,
can
we
hear
can hear
you.
you well.
Okay, thank you so much. Thank you for confirming that. Okay, so I want to welcome you to another statistical machine learning class. Of course, with statistical machine learning is like a story that goes on and on and on. But in preparation for some algorithms that we're going to use in statistical machine learning, we need to first understand some assumptions, and we need to understand basic foundational technique, okay, of statistical machine learning. And that is why our focus today is going to be on mathematics review. Let me tell you this, every algorithm, every statistical model, they are mathematical statements, okay? And of course, if we really want to understand the way the algorithm work, the way the statistical machine learning models work in general, okay, in order for us not to mislead, of course, we need to be able to get ourselves familiar with math review. In the outline, we're going to talk about vectors and matrices because most of the algorithms, I'm actually going to say 99% of algorithm, okay, they are vectorized. Uh, so we're going to talk about vector spaces, matrix operations. We're also going to talk about the Eigen decomposition. Okay, so talk about singular value decomposition. We're also going to talk about the mean vector, the covariance matrix, and of course, if you take a look at this material, we're going to use this material today and Friday, and that's why you see January 28th to 30. So uh, I want to believe today we only going to achieve outline number 1 to 3, while Friday we're going to focus on basic univariate optimization. Before I get started, I'm actually going to say this. I remember the other time I said statistical machine learning lies at the point of intersection of linear algebra, okay, statistics, okay, machine learning, okay, and basic programming, okay. I also going to say this. It's also, I think a calculus also fall in because the idea of calculus will be used in optimization. Because, you know, if one of our intentions or ambition is to optimize, we got no choice than to revisit our basic calculus. So I just wanted to understand all of that. There's something that I'm actually going to say. Okay. Uh, every statistical machine learning model, okay, is a mathematical statement. I think I said that before about the way data are generated. Now, let me tell you this. There's a because our data is random, we expect our model to reflect randomness as well. And that is why the idea of probability will also take a center stage. We got a lot of techniques, that are involved. Okay, I remember the other time I told you what is statistical in what we want to be doing. in, because it's statistical machine learning. What is statistical is is because the our statistics will provide us a way to learn from data and to do generalization. Okay, why do we need probability? Of course, the probability will be able to understand the uncertainty and randomness in the process. Okay, why do we need math review? Of course, we need math review because of the role of linear algebra. Most of the algorithm, they are actually vectorized. Most of them are vectorized. Most of them are in matrix form and stuff like that. So because of that, we need to be able to understand some basic assumptions. So let's start with the vector. This is an example of a vector, as you can see here. There's a column vector. Okay, we can also have a row vector. And this is an example of a matrix because algorithm, we applied algorithm on, maybe on high dimensional data or on big data. Okay, so I just wanted to take notes of that. Okay, which means the idea of matrix actually going to be used. Of course, we have some different there are special form of matrices that we're going to have. We're going to have a diagonal matrix. We're going to have an identity matrix. So that's an example of identity matrix. Then we actually, since we're going to be working with matrices, there's possibility. One of our intention may be to multiply two matrices. So as you can see right now, if I have a matrix A, so n by m, now I have a matrix B, it's n by k. Okay, of course they are actually conformable for multiplication if the numbers of column in the first one is equal to the numbers of rows in the second matrix. With that, I'm actually going to say they are conformable for multiplication. Let me tell you this. We don't want a situation where you've committed a lot of resources to your research, but only to be let down by poor statistical tool. And that is why uh, we are trying to let you know what you can do, what you cannot do. Okay, so that will be conformable for multiplication. Okay, so we're also going to have operation of matrix transpose. Okay, the matrix transpose, you know how we are able to convert rows of a matrix to column or converting column to rows. Okay, so if you take it, because maybe moving forward, maybe, oh, we need to transpose, we need to change the element. Why are we changing the element? Why are we changing the row to column? And why are we changing column to row? Because we want, this time to be in a very good mathematical standing for analysis or for computation. Okay, so we got some, and what is the notation, for transpose? At time we can use that. Then we can also use T. So it's the same. So that is a transpose. Okay, so we also want to be guided by properties. If I have a matrix, I find the transpose, and I find the transpose of a transpose. The transpose of a transpose will return the matrix back to its original form. Okay, the transpose, the transpose that you do second time will actually cancel out the transpose that you do the first time. And if I have two different matrices, okay, if I add them up, okay, and I find the transpose of that, it should be the same as the addition of the transpose of each. And if I actually, um, you know, find the matrix, if I multiply A by B and I find the transpose of the resulting matrix, it should be the same as this guy. Okay, we can verify all this. But you know what? I want to go into uh, another review, and I need you to pay attention. Where we are now is very, very crucial, okay, in statistical machine learning model. Let's talk about norm and inner products. We have inner product, we have outer product, but we're going to be focusing on norm and inner products, okay? Now, at times, we may want to figure out the length of a vector norm, okay? Now, I need you to pay attention to the notation that we're going to use. Take a look at this, okay? Whenever you see stuff like that, we want to figure out the vector norm, the length of the vector norm, okay? And if you want to do that, the S that you see here, okay, is actually talking about x1, x2 up to xn. If I want to find the vector norm is talking about the length. Okay, I want to figure out the length of a vector. Or what I'm just going to do, I'm actually going to square each of that. I'm going to add them up. I'll find the square roots. Okay, and let me tell you this. Instead of me to have this guy, what is this is in a scalar form. If I want to have this guy in a matrix form, then I'm actually going to do the transpose of S multiply by X. Okay? That is the way to do that in a matrix form. So this guy here is the same as this guy here. Because x1 will multiply x1. x2 will multiply s2. So x1 times x1 is going to be x1 squared. s2 times s2 is going to be s2 squared. And so on like that. So this is in a matrix form, while this is in a scalar form. Okay, that is what we call vector norm. Okay, we call that vector norm. That we call the length. Now, the next is inner product. Okay, when we're talking about inner product, I have two different matrices. Okay, and I find the transpose of one, then I multiply by the other. Of course, under X, I have X1, S2, S3 up to Xn. Under Y, I got Y1, Y2 up to Yn. Okay, with the inner product, X1 will multiply Y1, S2 will multiply Y2, and so on like that. So that's why you have this. Now, let me tell you this. So this is what we call inner product. Inner product has a meaning in statistical machine learning model. By the time we get to each topic that we want to talk about in statistical machine learning, you're going to see us talking about inner products. Okay, now the next thing is geometric interpretation. Okay, we may want to find angle between two vectors. We want to figure out angle between two vector. Okay, so if we want to figure out angle between two vector, this is the formula. Now, which means to figure out angle between two vector, okay, without inner product and without vector norm, then there's no way we'll be able to do that. If you take a look at the numerator, look at the numerator here. Okay, that's an inner product, right? If you take a look at the denominator, okay, take a look at this guy here. This is what? The vector norm for X, a vector norm for Y. Without you understanding the vector norm or inner product, you may not be able to figure out angle between two vectors. Let me tell you this. By the time we start principal component analysis, where we're trying to artificially create new dimension, we may want to see um you know the angle. We want to see the angle between two variables, because in statistical machine learning, if the angle between two variables is 90, it has implication. If the angle between two variables is 45 degree, it has implication. So right now, we need to, before we can actually understand statistical machine learning algorithm, we need to first internalize some basic mathematical provisions. Okay, is there any question before moving? I just talked about geometric interpretation now, where I want to figure out the angle between two vectors, and without the knowledge of vector norm and inner products, then we may not be able to move forward. Now, let me tell you this. Under principal component analysis, uh, initially we got a lot of features. Initially, we have a problem with high dimensional data, where you got so many variables, and you want to artificially create few dimensions, okay, which means you want to use a dimensionality reduction technique. And one of the assumptions, if you really want to know whether you have succeeded in, in fabricating artificial dimension, one of the properties, one of the assumptions is that any two principal components should be orthogonal. I'm going to say that again. Okay, by the time we get to principal component analysis, we actually want to make sure the new artificial variables created are orthogonal. Okay, they have to be independent. Okay, even though the original features they are not independent. Okay, and that's why we believe so many variables may be giving the same statistical information, and that is going to be problematic to the model. And that is why we're seeking dimensionality reduction technique. And the assumptions at the end of the day is your new artificial variables need to be orthogonal. What is the mathematical implication of orthogonality? Is that when x and y are orthogonal, okay, if the inner product is equal to 0, look at that. There's something that we call zero matrix. Situation where you multiply the transpose of x by y equal to 0, then x and y are orthogonal. Okay? Just wanted to take note of that. Okay. In statistical machine learning, we also talk about autonormal. Okay? We also talk about autonormal. Okay? I wanted to recall in your basic statistics, you've come across what we call standard normal distribution. When a random variable follow normal distribution, you have a mean, it has a mean and variance, right? Uh, but because of the fact that if I have a set of data from different setting, okay, and each of the data in this setting follow normal, this also follow normal, then I'm actually going to have several means. Okay. But if I actually want to restrict the values of the mean, okay, in each setting to be the same for effective comparison, I will go with standard normal distribution. The standard normal distribution is different from normal distribution. The standard, you standardize your normal distribution because you want to restrict the values of the mean and the standard deviation. So in standardization, you're going to say, okay, the mean is 0, the variance is 1. Okay, so we're also going to have the same in statistical machine learning, where we want to ensure the condition of orthonormal. Okay, what do we mean by that? Oh, this is what we mean. If I actually have a random variable s, I find the transpose and I multiply by x. If it is 0, okay, provided that I is not equal to j, and I look at the norm. Of course, you know how to get norm now. I mean the vector norm, which is the length, and I look at the norm equal to 1. This is like This is looking like in a standard normal distribution where the mean is 0, the standard deviation is 1. You understand what I mean? But right now we're looking into orthonormal. Okay, so the orthonormal property is guaranteed, okay, if this condition hold. Okay, but I'm going to tell you the implication of the orthonormality, okay, as you know, as time goes on. But right now, we just try to give you information. Let me tell you this. If basic mathematical properties are violated, then in your statistical analysis, okay, there's going to be an issue. And whatever recommendation you make will mislead. We do not want to mislead. And that is why we need to be mathematically and statistically guided. Okay, I'm moving. I want to move to function of matrices. Let me tell you this. Uh, in statistical machine learning, we may want to talk about the determinant. We talk about determinant of a matrix because I remember uh, when you are dealing with multivariate or regression analysis, without you knowing the determinant of a matrix, you may not be able to figure out the estimation of parameters. So, uh, uh, if we have a matrix, our data set in matrix, we can find the determinant of a matrix. And let me tell you this, when the determinant of a matrix exists, the inverse of a matrix also exists as well. Okay? So, and I also want to tell you, we're also going to have a square matrix when the numbers of rows and columns are the same. Okay? So in this course, we're actually going to be talking about the determinant of a square matrix. Okay, now I also wanted to know that if I have a product of matrix AB, the determinant of the resulting matrix is the same thing as the product of the determinant of A and the determinant of B. Okay? When the determinant of a matrix is 0, the matrix is singular. When the matrix is singular, you may not be able to figure out the inverse of a matrix because the existence of the determinant of a matrix will guarantee you computing the inverse. I just wanted to know that. Okay, there's something that we call trace. Okay, we're talking about trace when we have a matrix. Okay, a trace is talking about addition of the entries in the diagonal of a matrix. Okay, let me show you. Some of you may not understand what I mean by diagonal of a matrix. Okay, if I have this as a matrix, the diagonal here is actually here. If I add up elements in the diagonal, then I'm talking about trace. I just wanted to understand that. Okay, I'm moving. Okay, now we've been able to verify that if I have a square matrix, you know what I mean by a square matrix, where the numbers of rows and columns are the same. That's what we call square matrix. 4 by 4, 3 by 3, 5 by 5, and so on like that. And of course, the trace is just going to be adding element in the diagonal, and that's why you see A1, A11, A22, A33, until you get to ANN, which is actually talking about elements in the diagonal. Okay? Now, I think I've talked about this. At times, you could have three matrices that you multiply. If I multiply, say, matrix A by B by C, and I got another matrix. If I find the trace of what I got, okay, it is going to be the same thing as a trace of BCA. Maybe yeah, for first use B to multiply C before multiplying A. Okay, Please pay attention. You know what we're doing now? We're building up. We are building up to some statistical machine learning algorithm. Okay, we are building up. We are trying to understand, some basic operations that are going, that may be going on. Okay, so that's what we are exposing. That's what I'm showing you now. Now let's talk about matrix norms. By the time we start, um, there's this we call lasso regression. Okay, you're actually gonna come up with L1 norm, L2 norm, ridge and lasso regression. Okay, and that's why we want to understand what the norm is. The other time I show you what the vector norm. There's a difference between vector norm and a matrix norm. Let me go back before talking about matrix norm. Can I have a recap? Let me have a recap on vector norm. Can you see vector norm? The vector norm is different from matrix norm. So this is vector norm. Take a look at that. Now let's go to matrix norm. Okay. Now we want to talk about matrix norm, and specifically we want to talk about Frobenius matrix norm. Now, the only difference. Take a look at this. Can you see a squared? Okay. You still see a norm sum. You see that? A sign of norm. Okay. Now you see a square. Okay. In a scalar form, it is this. But do you know that a matrix norm will actually come from the product of two different matrices, but one matrix is coming from the other one. That is why, take a look at this. This guy here, a matrix A multiply by its transpose. Don't forget, I got this guy. Please pay attention. This guy, I got it from matrix A by transposing matrix A. The transposing matrix A means converting elements in the column to row, or converting row to column. And after I'm done with that, I use matrix A, which is the original matrix, to multiply it transpose, and I got a matrix. I got a new matrix. After getting the new matrix, then I look at the element in the diagonal and I add them up. That is the trace. And that is the matrix norm that we talk about. So we are trying to let you know the origin of whatever terminology or symbol or notation that we use in an algorithm. Okay, we can actually trace them to a particular source, which is what we're doing now. So if anybody tell you, okay, a matrix norm, okay, the matrix norm is just the trace of the product of a matrix and its transpose. Okay, now I want to go into matrix inverse, and I need you to pay attention now. Okay, a matrix inverse. But you know what? We are only concerned with the square matrix. Okay? If I want to talk about inverse, want to find the inverse of a square matrix that have the same numbers of rows and column. What is the notation for inverse? If I have a matrix A, okay, and I want to find the inverse, the notation is actually this. Do you know what this guy mean? That is inverse of matrix A. And let me tell you this. We have a formula for that. Okay? But you know what? You don't need to be worried about that, because you're gonna make use of software. But let me tell you this. Inverse, if I want to get the inverse of a matrix, the inverse of a matrix is the adjoint, the adjoint of the adjoint, the adjoint of A of a matrix A, okay, adjoint of matrix A divided by the determinant of A, okay, divided by determinants of A. Now, I told you something the other time. Oh my God. Situation where determinant equal to 0, you can see inverse is not going to exist because the data in the formula for computing inverse, okay, the determinant is at the denominator. When the denominator of a fraction equal to 0, that fraction is undefined. And that is why we said, as we said here, that situation where determinant is equal to 0, okay, then that matrix is actually not invertible. Okay, the matrix is not invertible, and in a situation where determinant is going to be equal to 0, then the reason why determinant is 0 is because the matrix does not have a full rank. There's something that we call a rank of a matrix. If I have a square matrix, a 4 by 4 matrix that have a full rank should have a rank of 4. A 5 by 5 matrix with a full rank should also have a rank of 5. Okay? 1 second. Okay, so now if I have a matrix and I've succeeded in finding the inverse, how am I going to know that I'm right? Okay? Please pay attention. How am I going to know if the inverse that I got is correct? We have a way to verify. The way to verify, I will multiply the inverse that I got with the original matrix. The moment I have identity, okay, then I'm right. What is an identity? For instance, if I'm working with 2 by 2, okay, if the matrix A is 2 by 2, identity is going to be this. Identity is going to be 1 0 0 1. Does that make sense? If I'm working with 3 by 3, identity will be 1 0 0 0 1 0 0 0 1. So whether I multiply the inverse by A by matrix A, or I multiply A by its inverse, if that inverse is correct, then the result should be identity. That's how to verify. Okay, I actually want to move right now to properties of inverse. If I have two matrices, please pay attention. If I have two matrices, I multiply A by B and I find the inverse. It should be the same as multiplying the inverse of matrix B by inverse of matrix A. So if I were you, why can't you try that and verify that? Okay. Now I'm going to go into number 2. Take a look at this guy. When I have a matrix A and I obtain the inverse, after obtaining the inverse, I found the transpose. It is the same thing as finding the inverse of a transpose, which is what I have here. These have been verified. Okay, another property. Okay, another property. If I if I if I actually if you take a look at this one, okay, if I find a product of A and B, okay, and I actually do the transpose in a negative way, okay, it's still gonna be that. You can verify that. But there's something that's also very important. If I find the determinant of an inverse, It is the same as finding the inverse of the determinant. Determinant of an inverse, the same as inverse of the determinant. Now, I want to go into what is of statistical interest. Orthonormal matrix. Orthonormal. Okay? Orthonormal matrix now. Okay? This is the condition. What if I give you if I ask you to investigate whether a particular matrix is orthonormal, okay, and begin to see assignment two, okay, those things like that. What would dominate assignment two is math review, okay. What if I give you a matrix and I ask you to investigate whether it is orthonormal? It is not all matrices that are orthonormal, okay. But how do I investigate that? What I'm going to do, I'll find the inverse, okay. I'll put that apart. That's what I'm saying. I'll find the inverse, put that apart, okay. I will go to the same matrix, original matrix. I will find the transpose, okay. Situation where they look the same. Then I'm going to say the matrix is orthonormal, okay. So, because in statistical machine learning, we could have some assumptions that has to do with orthonormality. And how do we investigate orthonormality? It's when the transpose of a matrix is the same as the inverse of that same matrix. There's a lot of information here. Okay, now I want to walk us through Eigen decomposition. Let me tell you this. By the time we start, uh, you know, uh, if our intention is about image processing or face recognition, or maybe we're looking into principal component analysis. There are some operations that involve decomposing matrix. Okay? Because we're going to believe that this particular matrix is heavy. Can we have a way to decompose matrix into two or more parts? Okay? Depending on our intention, I'm actually going to tell you now in principal component analysis, okay, it involves matrix decomposition. Not only that, okay, when I'm talking about topic module, or where from a combination of papers or the paper articles that I read, and I want to figure out what the topic is. Okay, it will involve matrix decomposition. And what we want to do right now is we actually want to understand how matrix can be decomposed the same way that when you were in high school, where you have a polynomial expression and you want to factorize. Factorizing a polynomial of degree 3, you're actually going to have three separate terms. So this is synonymous with splitting or decomposing matrix into components. We're going to talk about that. Okay, so if I have a square matrix and I want to do Eigen decomposition, particularly in principal component analysis, the Eigen decomposition we're actually going to have a way to decompose your matrix into the combination of eigenvectors and eigenvalues. Okay, so if you take a look at what I have here, okay, I have a matrix A n by n and x n by 1, and that's equal to lambda s. Okay, if you take a look at what I have here, decomposition will enable us to solve to make the equation to have very easy way to figure out. Okay, and if lambda represent the eigenvalues, okay, and I'm seeking a characteristics rules. I actually want to find what is the values of each eigenvalue. Okay, I can do this. Okay, I'm going to solve this equation. This is a matrix A minus lambda I, where I is an identity. Okay, at the end of the day, I'm actually going to figure out the values of lambda. Okay, depending on the dimension of A. If dimension of A is 2 by 2, then I'm going to have two different lambda values, lambda 1, lambda 2. If the dimension is 3 by 3, the lambda will be lambda 1, lambda 2, lambda 3. Okay, so I'm just letting you to see that. Okay, the determinant now in terms of eigenvalues, the determinant of A is just the product of eigenvalues. For instance, if A is n by n, if a matrix A is n by n, is a square matrix, okay, the determinant of A is the product of the eigenvalues. Lambda 1 is an eigenvalue, lambda 2 is an eigenvalue. Then the trace of A is the addition of eigenvalues. You can see that if I multiply eigenvalues, I actually want to figure out determinants. Don't forget, I need determinant to exist before I can figure out the inverse of a matrix. But if I add eigenvalues, what am I looking for? I'm looking for trace. What is the significance of trace? Maybe I want to know the general variance. The total variance. Because each eigenvalue represents the variance of a particular principal component. Okay, when A is positive definite, what do we mean by that? Okay, if you want to verify, we're talking about strictly greater than zero. That's strictly greater than zero. We have a positive definite. We have a semi-positive definite. Semi-positive definite, okay, that will include equal to zero. Okay, so if you take a look at what I have, okay, for positive definite, we're trying to say eigenvalues, each of them must be strictly greater than zero. Don't forget, each of them represent variance. We want them to be non-negative. Not only that, we want them to be strictly zero. I mean, to be strictly greater than zero. But we can also have situation where they can be zero. Then in that one is what I'm going to show you now is this guy here. And you know what we call that one? Positive semi-definite. Okay? That situation where we can tolerate one of the eigenvalue to be zero, and there are situations where we can't tolerate that. I want to believe when we start optimization, okay, in optimization, okay, where we expect it to be strictly positive definite for global minimum, okay, we're still going to talk about all of that. Okay, so eigenvalues has to be strictly positive. We're giving you information now. Okay. I think I've talked about all of this, So in eigenvalue decomposition, uh, we have this condition of orthonormality must hold in look at this. I talked about this the other time. When the transpose of a matrix equal to the inverse, that is orthonormal. Okay, orthonormal is a condition that must be guaranteed if I want to talk about eigen decomposition. Now, let me now walk you through eigen decomposition now. Okay. We use eigen decomposition. We use that in principal component analysis. Now take a look at this. I have a matrix A. This matrix is too heavy. I want to decompose it. Okay. And then I'm decomposing it into what? Three different matrices, simpler matrices. What does each of these represent? I'm going to tell you now. This guy, one second. This guy is a diagonal eigenvalues. The diagonal values. Okay. But what does Q represent? Q represent eigenvector. The Q here the transpose of eigenvector. So in principal component analysis, when we decompose a matrix A, do you know what the matrix A is going to be? By the time we start principal component analysis, the matrix A will be a covariance matrix. Covariance matrix. Okay, so when we perform an eigendecomposition of that, that will give us eigenvectors and eigenvalues. Then what do you think eigenvectors represent? Eigenvectors represent the artificial dimensions that you create. We're still going to talk about all of that. But you know what? Based on this, I can ask you to do this. This is matrix A, okay? I can say, can you obtain the eigendecomposition of that? Eigendecomposition is actually saying decompose it into these three, okay? There's a way you can do that in R, okay? My TA will walk you through all of that. Okay, I want to move. There's something that we call singular value decomposition, okay? We are still decomposing matrix, okay? When you are decomposing, when you are using the singular value decomposition, you have a matrix A and you are splitting that into U, D, V, the transpose of that. Okay. Now, I said here, there is an autonomous square U. U is n by m and V is n by n. Then the D is a diagonal. But let me tell you this, when you are using singular value decomposition, okay, in the diagonal, okay, we expect each of the values in the diagonal to be strictly greater than 0. Okay, so that's exactly what I mean. And let me tell you this, because I have D1, D2 up to DR, the rank of the matrix must be R. But in image processing, in image compression, we are not going to use a full rank. When you have your image, okay, that you have not compressed, the image as a full rank. When you compress the image, then it doesn't have a full rank. So what we want to do, we actually want to reduce the rank. Okay, we want to compress the image and still ensure that we do not lose total information. The quality is still going to be guaranteed. Okay, that's what I mean. I've talked about this. Now, take a look at this. If my image has a rank of R, every image is a matrix. Image has rows and column. Okay? But because of the fact that I do not have enough space, because more pixels, you need more storage space. And what do we want to do? We want to reduce the number of pixels in an image. But to reduce the number of pixels in an image, we don't want the quality to be affected. So it means we actually using a singular value decomposition, the rank is not going to be R anymore, but the rank is going to be K. We're actually going to choose the best. We're going to choose the top one. Maybe instead of us to go from D1 to DR, we're going to go from maybe D1 to D5, few ones. And that's why you see K. So, and that is why we call that best rank K approximation to A. So all of these will be in use. Because I said this material, we're still going to use it on Friday. I think I'm going to start from here on Friday. Is there any question before I go today? Is there any question before I go today? Okay, let me give this information. Monday, our lecture will be on Zoom. We're not going to be here in person. And let me be sincere. Let me tell you what happened. My daughter secured a full scholarship to University of St. Thomas, and she also do track. So University of St. Thomas is coming to their high school to do signing. and they expect me to be there. So it's gonna take place at 7 to 9. And to come from Blaine High School to drive here, I will miss lecture. So I will have it on Zoom on Monday. But I will make an announcement. But on Friday, we are meeting here in person. Make sure you all stay safe and have a lovely day. Bye for now, everyone. Yep. Exactly. 10:50. I forgot to announce, but that would be true. Make an announcement.